Hello everyone and welcome to another video. And I talked about in a previous video where I was talking about in a previous video that I would maybe make some videos about ray marching, and which is something that I've been doing a lot recently. Um, so um, let's do this. This is the part one of me teaching you how to do ray marching. And if you're not familiar with ray marching or you've never heard it before, I'm going to show you some things that you can do with it. For these series, we're going to use something called ShaderToy, which is a website where you can write shaders. Now, we could have done this like using our own OpenGL application running natively on our machines, but we might do that later in this series. But to get started, it's just the ShaderToy is the easiest way to get started in this case. So first of all, let me show you some things that I've been doing with ray marching. Zoom in a little bit. This is my most recent work. Let's see. So this is like a house. And yeah, and then we have, let's see, I made a swimming pool. You can also use the mouse here to look around. Let's have a look at one more. Let's see. I did make this one I'm pretty happy about. It's a little airplane. So you can do a lot of stuff with ray marching. And before we start actually writing some code, let me just explain to you shortly how it works. It's actually really, really simple, and that's why I love ray marching. So let's draw a little bit. So let's say we have, let me just zoom out a little bit. Let's say we have your monitor here, your screen. I'm not very good at drawing, and here we have, here's you sitting at your screen. Maybe you're wearing a cap or something. And you're looking at the screen, and we want to render a cube here on the screen, for example. So inside our screen here, we have a scene, and the scene might have a cube. So in order to render this cube onto the screen, for every pixel on our screen, you know, a screen is made up a bunch of pixels, we step into the scene with a fixed number of steps. So let's just see these green lines here as steps. And you know, we do this for every pixel. I'm not going to draw them all. And for every step, we call a function to get the distance into the scene. So we might have like a function called get dist. And this function will take in a vec3 point, and it will return a float number representing the distance into the scene. And in this case, we only have one thing in the scene, so we're only going to return a distance to a box. And we call this function for every step. So in this step here, we're going to make a call to this function. And for this step, we're also going to do that. And for this step, we're also going to do that. And we're going to do this until we reach a certain threshold for when we consider the box to be close enough. So we might, define some kind of a threshold for when we consider the distance to be small enough. For example, we might have 0.003 as a threshold. And when the distance is close enough to this number, we're gonna break out of the loop where we step into the scene, and we're gonna render whatever this ray here hit. So in this case, this line here is going to hit somewhere here on the box. So we're gonna compute the color for this pixel here and make some beautiful imagery out of that. So that is basically how ray marching works. And yeah, let's just get into it, I guess. So let's go to ShaderToy. ShaderToy is free. You can just create an account, or actually you don't have to create an account to write shaders here. You can just go to ShaderToy and click the new button here. And this will give us this default shader here that we can modify. Let's just see. It's a little bit too... I hope you can see this good enough. Maybe we'll go with that. So this is the default shader. So let's just remove some of the stuff here because we don't need most of it. We're going to want a color that we're going to render, but let's just make that black for now. So now I made a change here, and if I want to see the change, I can either click the compile button here, or I can hit Alt-Enter, and we should see just a black screen, and I can color it if I want. I can make it a little bit green and a little bit blue. Yeah, you get the point. And this is the GLSL language, by the way, which is what we're using to write shaders. Now another thing I like to do is to make some global defines that I can use later to make the coding a bit simpler. And I also like to change this value here to something shorter. Now this is the coordinate, the current pixel coordinate into the screen here, and it's fragment. It's short for fragment coordinate. I'm gonna rename this to FC because it's shorter and it's easier to use later. And we're also going to define a definition here for resolution. I'm just gonna call it R. So define R, iResolution, just so that I can more easily do that later. So now if I recompile, nothing will change, but let's just color the UV coordinates. Let's make the color of the screen the UV coordinates. So let's do col.rg plus equals UV, and we can see the UV coordinates. And when we're doing ray marching, we want the UV coordinates to start from the center. Right now they start from the bottom left corner. You can see it's very dark down here. That's because the UV coordinates approaches 0 down here, but we want them to approach 0 into the center, at the center of the screen. So to do that, we can do, instead of dividing by resolution.xy, we can do minus 0.5 times resolution.xy. So we're moving the fragment coordinate backwards half of the resolution. And then we want to divide this whole thing with resolution.y because that will fix the aspect ratio. So now if we hit enter, we should see that the UV coordinate starts from the center. Now they're still dark down here. It's because they're getting negative down here. if we were to do the absolute of the UV coordinate, we can see that the center is here. Okay, cool. So now we have the UV coordinates that we want. Now in this video, we're just gonna simply render a, we'll start by rendering a sphere because that's the easiest thing. And hopefully we'll also render a cube in this video. So first of all, we're gonna need some other defines here. I talked about the threshold we want to use for when we consider the ray to be close enough to the surface. So let's define that one. So I'm just going to do a define. Let's call it near. And we also want a far for when we consider the ray to have missed the geometry. So for example, maybe a ray down here will completely miss the box. And if we have a threshold for how far a ray can go, we can break out of our loop quicker, which will make our code faster. So maybe we have a threshold of 100. Where we say that if the ray reaches this far, we're just going to stop. So let's define a far. Let's make it 100. And we also want to have a define for how many steps we're going to do. For this example here, we're just going to put 100. Now this should be an integer, so don't put any floating points here. And depending on what kind of machine you're running, you might need to modify these values a little bit, because if you're running on a very slow machine, maybe you don't want to have these many steps. Oh, I forgot to type steps. Maybe you want to lower it to like 40 or 50 or something. But I'm going to use 100 here for now. Okay. And then we're going to actually write our ray marching loop. So we'll start off with the marching loop just giving us the distance, or returning the distance, or returning a boolean. Sorry, it returns a boolean if it hits the thing or not. So let's do bool march, and it's going to take in a ray origin and a ray direction. And then we want to store somewhere how far we have traveled. Let's just call this d for distance, and we're going to start by 0 because we haven't traveled anywhere yet. And then we're going to loop, and we're going to loop step many times. And then we want to get the so for every step that we're doing, we want to know where is the current point of this step, basically. So let's make it red. We want to know the position of this step here, which will be a vec3. We want to know the position of this so that we can use that position to get the distance in the next step towards this box here. So to get this point, we can just do vec3p is equal to ray origin plus rd, ray direction, times the distance we have traveled. And this will be the current point. And now we have to get the distance into our scene. And we haven't written this function yet, but let's just assume that we've written it for now. So we're going to do float next. This is the next distance is equal to get dist, and we're going to put in p. And then we're going to add this next value to the distance we have traveled. So we're going to do d plus equals next. And then we want to check if next is less or equal to our near. Then we have obviously hit something, so we're going to break. And if next is greater than or equal to far, then we've missed the scene completely. So we're going to return false. And if we end up here, we have hit something, so we can return true. Now we need to implement this getDist function. So float getDist, and it's going to take in a point. And this is basically the function that describes our scene. Maybe a better word for it would be scene. So let's just rename it to scene. And here we can basically decide what kind of shapes we want to render. And as I said, we're going to start by rendering a simple sphere. And for, each shape that we want to render can be described using a signed distance function. So, for example, if you want to render a sphere, this sphere can be described as the length of the current point minus the radius of the circle or of the sphere. So for every point, the distance will be the length of the point minus the radius of the sphere. And this is a signed distance function. You also encountered this short version of that name, SDF. So we want to create an SDF for a sphere. So let's do float sphere SDF, vec3p, float r for radius, and we can just return the length of p minus r. Okay. So now in our scene here, we can simply do float sphere is equal to sphere SDF p, and a radius that we want to have, let's just make it 1 for now. And we're going to return sphere. And later we could add other shapes in our scene function here. But for now we're just doing a sphere. Now we have implemented this scene function here. And let's hit save and see if things are compiling. It did not. Step is undefined. Should be steps. Cool. So now we have our March function ready, and we should be able to use that very soon. So let's go down into our main image here. And this March function takes in the ray origin and the ray direction, which we haven't defined yet. So let's define the ray origin down here. I'm just going to make it 0, 0, and maybe step back away from the screen a little bit. So I'm going to do minus, let's make it 4. And the ray direction is simply normalize vec3 uv.xy and 1. And let's actually see what this ray direction looks like if we put it as a color. So col plus equals rd, and you can see it looks something like this. So now we're ready to march. So we can do if march ray direction, ray origin, ray direction. Let's just make col plus equals 1. And there we have our sphere. Now it doesn't look like much right now. It just looks like a 2D circle. So let's make it a bit more, look a little bit more 3D. And to do that, we can compute some extra information from this March loop here. So what I'm going to do is actually I'm going to define a struct, which is some data that this March function will give us. So let's just call it data. And I want this function to give me the the point where we hit the sphere. And later we also might want to know the normal. I'm going to explain what a normal is shortly. And we want to know the distance. So point, normal, distance. And now what we can do is in our March function here, we can put in out data data. And what this will do is that it will take in the data. And since we have an in out here, it will allow us to modify this variable inside of here so that when the March function returns, we can use this variable here to extract the data. So now we have to obviously create an instance of this data down here so we can pass it into the March function. So let's just do data data is equal to data. And we have to populate it with some values. So we have the point, normal, and the distance. And I'm just going to make those 0. Like this. And then in our March function, we have to pass in the data variable. And if we recompile this, nothing will change for now because we haven't done anything with the data. But now we can populate this data here. So first of all, we can grab the point. So point is equal to ray origin plus ray direction times the distance we traveled. And let's just put this on the data for now. So data.p is equal to p. And what if we now, down in our main image, we do call plus equals data.p. You should see some colors going on here. Now, a more useful thing to extract here is the normal, because we can do some more interesting stuff with that. So what is a normal then? So if we go back here and draw a little bit, let's say we have a box. Again, I'm terrible at drawing. The normal is just a vector that's pointing, that tells us where the face is pointing. So for example, this face here of the box is pointing upwards. This face here is pointing to the right. And this face here is pointing towards us, basically a negative C value. And this face here is pointing to the left. And this face in the front here is pointing into the screen, a positive C value. And these are just vec3s. So for example, this vector up here is going to be vec3, 0, 1, 0. And this point in the front here is going to be 0, 0, 1. And this point here is going to be, or this vector here is going to be 0, 0, minus 1. Because this is the x, y, z. So that's all what our normal is. And we can use this to do some lighting and stuff like that in our scene, which we will get into later. So how do we compute the normal? We can do a little trick. So after we're done calculating the p here, the position, we can do vec2, and we're going to define some kind of epsilon, because what we're going to do is calculate the distance at the current point, but we're going to shift a little bit from left, right, up, down, so that we can get like an interpolated normal using our distance function. And we want to, this vec2 will let us describe how the radius of which we're interpolating the distance from. So For example, how far are we going to look to the right? How far are we going to look up, etc. So what we can do is I'm just going to call this E, short for epsilon. And let's just make it 0, 0, 0. Depending on how big you make this number, the smoother your normals will be. But they will be more accurate the smaller this number is. Let's just make it 0.01, something like that. And we are only going to populate the x component of this vector here, because we're going to use this. We're going to use this epsilon using a Swizzle. I'll show you what that is in a moment. So now we can calculate the normal by doing vec3n is equal to normalize sin p minus vec3, and then we're going to do sin p minus e dot xyy, sin p minus e dot yxy, sin p minus e dot yx. So what this is doing is basically, here we're subtracting 0, 0, 0, 0, 1, 0, 0. We're subtracting this vector from the point, and here we're subtracting this vector, and here we're subtracting this vector. So you can see that here we're looking a little bit to the right, and here we're looking a little bit upwards, and here we're looking a little bit into the screen. And this will give us an approximated normal. So if we hit recompile, nothing should change right now. But now we can put this n value on our data here. So we're going to do data.n is equal to n. And we can also put the distance, and we have the distance here. So we can do data.d is equal to d. So now what we can do is down here in our main image, we can do, let's just see what the distance will give us. So if we do data.d, this will give us the distance. Now it looks pretty much all white, but if we divide this by our far value, that didn't actually do anything right now. Let's just multiply it by a smaller number. Yeah, it doesn't really give us anything meaningful right now, but later we can sort of use this to create fog and stuff. I don't know if you can see it on your screen, but on my screen it is a little bit darker at the center here, and that's because the center of the sphere is closer to us. Maybe if we raise this to some larger number and scale it down a little bit. Yeah, now you can obviously see that it's a bit darker here. But we can also do col plus equals data.n, which is the normal. It kind of looks like the data.p. It's pretty much identical. But we can use this to do some lighting. So for example, let's say we have a light direction. Let's just call it L, where the light is coming from. And let's do normalize vec3 1, 2, minus 3. This will make it so that the light is coming from behind, basically from behind our back, but slightly to the right and a little bit upwards. And now what we can do is use this to put some light on our sphere here. Maybe we can also define a light color col is equal to like 3. Let's just make it pretty red, a little bit green, and a little bit blue. I think this will give us a little bit of a yellowish color. So now what we can do is we want to know how much light the surface of the sphere will receive from our light source. So what we can use is the dot product between the normal and the light direction. So we can call this n.l, which is going to be the dot product between data.n and l. Now, this will tell us how much the face of the sphere is facing the light, basically. But this dot product can also give us a negative number if it's facing the complete opposite direction. So what we're going to do is, we don't want negative numbers here, so we're going to do max 0. So that if it's negative, we're just going to get a 0. And then we can do col plus equals light col times n.l. And now it's starting to look very 3D. So here's our sphere. And maybe we should also apply some kind of texture or something to the sphere just so that we can get some detail here. And for that, we're going to need a UV coordinate. Now, I kind of talked about UV coordinates earlier. So here we're computing a UV coordinate, which is a normalized coordinate between, usually between 0 and 1, that represents where on the, which pixel on the screen we're at, or which fragment on the screen we're at. And in ShaderToy here, you can actually, there are some pre-made textures that we can use. So if you click on one of these boxes down here, I'm going to use iChannel 3. It's a little bit small for you, but it says iChannel 3 here. So I'm going to click here, and you can click textures. And let's just grab some texture here. And let's just grab, we have this rock tiles texture. Well, let's just try to fill the entire screen with this texture first. And I don't want to use these UV coordinates here because they are from the center, or we can try using them, but it might not look the way we expect it to look. So I'm just going to comment this out here for now, so we just get a black screen. And I'm just going to show you how we can use this texture to fill the entire screen. So to do that, we can simply do col is equal to texture, and it's going to take in the channel that we put the texture on, which is iChannel 3, and a UV coordinate. Now this texture will return a vec4, but our color is a vec3. And the reason it returns a vec4 is because it contains a vec4 red, green, blue, alpha. But in this case, we only care about red, green, and blue. So what we can do is simply do .rgb to only get the red, green, and blue. And if I hit enter now, we should see this texture here. And actually it doesn't look that bad. I'm just going to have a sip of, I'm getting a little bit thirsty. So that's how you get textures. Now we want to put this texture onto our sphere. So let's remove this for now. And let's bring back our sphere. So we need to know the UV coordinate on the sphere to put this texture there. Now there are multiple ways to get the UV coordinate. One naive approach would be to just use the point on the sphere that we got here, P. So let's just try that first. So we can also define here a, let's call it albedo. Albedo is the name in 3D graphics or in graphics in general. Albedo is the name of the base color of a material, basically. So in this case, we want to use this texture here as the, the diffuse color of this sphere. So I'm just going to call it albedo is equal to texture I channel 3, and I'm just going to use data.p. Now this is a 3-dimensional vector, and UVs are always 2D, unless you're working with like a 3D texture, but this is a 2D texture. But let's just, for example, grab the X and Y component of that one. And once again, we're going to do .rgb. And when we do our calculation here for the light, we can also add the albedo into the equation by applying the albedo with this. Now it doesn't look that bad actually, but I'm sure if we were to rotate this, it might look a bit weird. So how do we rotate this sphere? The way we can do that is, first we can describe our rotation using a 2x2 matrix. So let's just define a rotation function up here, which will return a 2x2 matrix. Let's just call it rot, and it will take in a angle. And we're going to need the cosine of this angle. I'm just going to call it C. And we're going to need the sine of the angle, S. And then we're going to return mat2 C, S minus S, C. Now, if we want to learn more about matrix math, maybe I'll make another video about it. But basically, we can use this matrix, we can multiply components of our vectors using this matrix to rotate it. And this matrix just describes how much each component in that vector will be rotated, basically. But yeah, this is a very useful function. So now let's go down here, and actually, instead of rotating the sphere, let's rotate the camera. So in order to do that, we would need to, we could use the mouse to rotate it, but let's just use the time for now so that it just automatically rotates. So what we want to do is rotate the origin first. So we're going to do rho dot, and we want to rotate around the y-axis so that the sphere, imagine the sphere like this, and we stick some kind of pole into the sphere like this, and it goes out on the top. So let's imagine we made a hole into the sphere, and we want to rotate the sphere around this pole. So this is the y-axis. So in order to rotate around the y-axis, we're going to need to rotate the x and c component. So we're going to need to rotate the x component and the z component. So, and as I said, we're going to rotate the camera instead, but it's going to give us the illusion that the sphere is rotating kind of. So we can do rho.xc times equals rotate. And in ShaderToy, there is a global input variable for time, which is itime. And we're also going to need to rotate the ray directions. We're going to do rd.xc times equals rot itime. And now if I hit compile, we should see the sphere rotating. And you can see it looks a bit stretched. But instead of using time, let's use the mouse instead. And similarly, there is a global input variable called iMouse to get the position of the mouse. But we want to use a normalized position of the mouse, similar to the UV coordinate here. So we're going to do vec4m for mouse is equal to vec4, because the mouse is a vec4, because the the X is the X position of the mouse. So this is mouse X, mouse Y. And then we have the C component, which is if the mouse is pressed or not. So press. And the W component is if it's clicked, I think. But we want to normalize the X and Y components. We're going to do iMouse.xy minus 0.5 times resolution.xy divided by resolution.y. And then we're just going to populate the two extra components with the mouse CW. So here we have our mouse. Now we can use the mouse to rotate the camera instead. And for this, we're going to need some other defines here. We want to have pi and tau. So pi is defined as, we can define an approximation of pi, and let's call it, let's do just 3.14159, I think it is. I haven't memorized all of the decimal points, but it's something like that. And then we have tau, which is just pi times 2. And we can use the tau here to rotate. And the reason we want to use tau is because it will make sure that we rotate a whole circle around the clock, basically. So instead of time here, we're going to do m.x times tau. So now, if I click and drag, I can rotate the sphere like this. Now it's a little bit dark here because the light isn't hitting the back. So what we can do is add some ambient light just to actually be able to see the back here. And to do that, in our n.l calculation here, we can just do a maximum of like 0.1, 0.5 maybe. Yeah, you can play around with this however you want, maybe 25. So now we can see some of the back as well. And you can see the sphere is a little bit stretched here. Now there is a better way to get the UV coordinate for a sphere, which is a spherical UV coordinate projection. Just to not, this video is already a bit long, so maybe we shouldn't do that right now. I promised that we were going to render a box as well. So what we can do to, let's just keep the sphere as it is for now, and maybe I will definitely go into how to compute better UV coordinates for a sphere in another video. But now we can, we want to render a cube. So we have our sphere SDF, and we want to have a cube SDF as well, or a box SDF. So let's do box SDF, and it's going to take in a P position and a size. And here we want to do P is equal to abs P minus S. So we're taking the absolute of P, because it can contain negative values as well. And we're moving it away from the size a bit. And then we're going to return length max P 0, so that after we have subtracted the size from P, we might get negative values. So we're going to ensure we don't get negative values by putting a max 0 here. And then we're going to do plus min max p.x max p.y p.c and 0. So what this is doing is, as I said, we've moved the sphere back from the size, the absolute position of P. And since we're stripping away the negative values, we're gonna get sort of half of the origin is gonna be sort of half of the box, and then we're adding the maximum value of the components, what's left after the subtraction, which will give us the distance to a box, basically. So now inside of our scene here, let's comment out sphere. And let's do float box is equal to box SDF. And we're going to put in P and the size of the box. And I'm just going to make the box maybe 0.5 in size. And by the way, if I put just one floating point value inside of vec3, it will fill all of the components with 0.5. So for example, I could do this, but doing this is the exact same thing. And then we're going to return box. And here we have a box. Let's make it a bit bigger. Let's do 1. And now we can see that the UV coordinates are definitely distorted. So let's make some proper UV coordinate calculations for this box. And we can define a function for this. So let's do vec2 box UV. It will take in a point and a normal. And before we do anything crazy here, let's just play around with this a bit. Let's actually put it down here. And actually, before we do that, I'm just going to show you some things. So if we go down to our march here where we get the albedo, right now we're grabbing the XY component. So if we think about like a plane like this, the XY component will be X is down here and Y is up like this. So that's the reason why these UV coordinates only work for the front of the cube. For example, if we wanted to UV coordinate for the right side of the cube, we would have to grab the, if we think about the cube like this, that's a really ugly cube. The UV coordinates on this side will instead be Z. So this will be Z, and this will be Y. Yeah. So if we instead change that to ZY, we're going to get that face here, but we're also going to get the face on the other side there. So it will work for both sides. But we want this to work for all of the sides. By the way, before we do that, maybe we should make it possible to actually see the top side as well. And that's really easy. When we rotate the origin and the ray here, we can also do rho dot yc times equals rot m dot y times tau, and rd dot yc times equals rot m dot y times tau. So now we can rotate like this. So we want to get this UV coordinates to work on all of the sides. And doing that is pretty simple. Let's go get our box UV back here. So the norm, as I told you previously, the normal tells us where the face is pointing. So we can use this normal to decide which components of the point vector that we want to use. So one naive approach of doing this would be like if n is equal to, so if we're on the right side of the box, return p dot cy, else, but this is a bit, often when writing shaders, we don't like having if statements, but that's a topic for a completely different video. So we can do this in a little bit better way. We can use the mix function, which is basically like lerp, if you're familiar with lerp. So lerp takes a number, takes in three numbers, one starting point number, let's say 0.2 and 4.5. And then the third argument is how much do we want this value to reach this value, basically. So if I would do 0.5 here, it would go halfway to 4.5. If I were to do 0, this would just return 0.2 because we're not reaching anywhere towards 4.5. If I were to do 1, this would return 4.5 because we're reaching all the way to 4.5. And mix is the exact same thing. So what we can do here is return mix, and let's start with p dot xy, and we want to mix that with p dot cy, and then we can use the dot product of the normal to know which side we're on, because as I told you, the dot product tells us how much a vector is pointing towards another vector. So what we can do is, as I told you, they can also return negative numbers. So we're going to do max 0.0 dot n vec3 0 0 1. So in this case, we're going to return p.xy, which I told you before is like the UV coordinates for the front of the cube. But we're gonna interpolate towards p.cy as how much this the normal is pointing towards the right side of the face. So let's just start with that for now. Let's compile. Nothing should change right now. And if we go down here, and instead of putting in data.p.cy, we can do box uv data.p data.n. And now we should see that, yeah, it still doesn't look right. Let's see here. Did I do something wrong? cy. Oh, sorry, this should actually be like this, because this is pointing, towards the front face or back face, but we want to check how much it points to the right face. So now if I recompile, we should see that the UV coordinates works for some of the sides. And actually I did make a mistake here, because this should actually work for all of those sides right now, except for the bottom and top. So instead of using max here, we're going to use the absolute. So we can do abs. And now the UV coordinate should work all around the cube, except for bottom and top. And to fix this, we can wrap this in another mix. So we're going to mix this mix with another mix. And the other mix will be p dot, let's see here, it's going to be p dot xc, and we're going to do the same thing here, abs dot n, and we want to see how much it points either upwards or downwards. So we're going to do 0 1 0, and let's just make this a bit prettier. And now if we recompile, it should work for the top and bottom as well. And there we go. And one last thing before we end this part of the video is I want to show you how you can render, we can render both shapes here actually. But first let's just pull the camera backwards a little bit so we can see more of the scene. So on our ray origin, I'm going to do -8. So we're stepping back a little bit. And then let's bring back the sphere here. Now, instead of returning sphere and returning box. We're going to remove those so we have both sphere and box. And in order to render both, we can simply return the minimum of those values. So we can do return min sphere box. Now the sphere is probably inside of the box. That's why we can't see it. So we need to move the sphere away from the box a little bit, or move the box away from the sphere. It's whatever you like. So in order to move the sphere, we can, when we do sphere SDF, we can simply subtract some position here. So let's do maybe 1.5 on the X, 0 on the rest. And now we got the sphere over there. Let's move it a little bit more. So now we have both of the shapes here. Pretty cool. And hopefully in the next video, I will show you how to get better UV coordinates for a sphere. It's actually also pretty simple. Actually, why not? Let's just do it for now. Let's just do it now. Why not? So we can do vec2 sphere UV, and it's going to take in the same thing. So we actually only need the point, I think, and then we can do float u is equal to acos p dot x, float v is equal to a tan p dot y p dot c, and then let's see if I got this right. Then we have to do u is equal to 0.5 plus u divided by tau, I think, and v is equal to 0.5 minus v divided by pi. Hopefully I got that right. And then we can return vec2 uv. And let's just get rid of the box for now. So let's just return sphere. And let's go down here, and we can do, let's just copy this and comment this one out. And we can do sphere uv data.p, and that doesn't look right. Let's do, I think we actually have to take in the normal. Yeah, that looks better. Look, we can scale it up a little bit. So let's do, oops, my keyboard sometimes plays tricks on me. 1 second, there we go. Times 2. And you can see, actually let's remove the offset here. And maybe make the sphere a bit bigger. These are more spherical coordinates. Now it looks a bit ugly down here because you know, the UV coordinates has to reach 0 somewhere, and they're doing that here. Now we could play around with the sphere UV a little bit. For example, sometimes, yeah, that actually looks better. And if you want this UV coordinates to be originated like from top to bottom instead, we can just change these to YC, I think. No, wait, Y, X, yeah. And then the origin will be at the top instead. So these, I don't really like the patterns that spherical UV coordinates give me where it reaches 0, but you know, it's probably the best you can do. Now we could also try, if we go back to the box UV, sometimes it actually looks kind of good, but in this case it doesn't. Now you could fix this because when we do box box UV, we're taking the dot, we're using a dot product, and a dot product goes from 0 to 1. But we can sort of make it more drastic by rounding this. So if we round this call, we're getting a little bit more pleasant UV coordinates. Now in this situation, these coordinates actually look better than the spherical UV coordinates, because we don't get those ugly stretchy parts at the origin. However, we should see some seams here and there. I think here's the texture seam, and here. But yeah, it's like an artistic decision if you want to use the box UVs or the sphere UVs. Let's bring back the box as well. And let's give the sphere some offset. Make it a bit smaller. And here we have both of the shapes. So I hope you enjoyed this video, and in the next videos we will do some more complicated stuff. Thank you for watching.